For the remainder of this module, we'll give a brief introduction to the idea of energy changes during reactions. This is the subject of thermodynamics. Now, if we look at that word, thermo does not mean temperature, but rather energy in general. And if you're dynamic, that means you're changing. So thermodynamics is the study of energy changes. Our discussion of energy changes will also lead us to the concept of equilibrium and to the area of kinetics. Energetics is the first of three major issues we will work through in reactions. In the rest of this module, we will look at how a chemical system can transfer energy to its surroundings through heat and work. We will then spend a module focusing on the heat portion with a quantity called enthalpy. This will be related to the bond energies of bonds that break and form during a reaction. When enthalpy is combined with entropy, we get the free energy of a process, which addresses whether or not a reaction will go. This will be the third module. If a reaction is reversible, we can ask, how far will it go? This gets us to a module where we will address equilibrium. We might also ask, how fast does it get there? This will be a module on kinetics. And finally, we can ask if there is a way that we can control where a reaction ends up. This will be where we will finish our general discussion on reaction energetics. Everything has energy. There's potential energy present in atoms with the interaction between electrons and the nucleus. In molecules, when bonds form, the potential energy changes. In materials, intermolecular forces are based on charge interaction. There's kinetic energy as well, with electrons moving in atoms and molecules moving in materials. Thermodynamics is interested in the energy of the universe, but we are trying to focus on a specific process, which we call the system. For chemists, the system is usually a chemical reaction. Everything else is called the surroundings. So we pay attention to how energy transfers between the system and the surroundings. And we start with what is called the first law of thermodynamics. We start with the first law of thermodynamics, which is essentially the law of conservation of energy. It states that delta E of the universe equals 0. When we see the capital Greek delta in thermodynamics, it means the change in. According to this law, the energy of the universe does not change. But the thermodynamic universe is made up of our system and its surroundings. We're concerned with the transfer of energy between our system and its surroundings. The energy of each can change, but the total energy change still has to equal 0. So we rewrite the first law as delta E of the system plus delta E of the surroundings equals 0. Rearranging, we find that delta E of the system equals negative delta E of the surroundings. This does not mean that delta E of the surroundings is always negative. No. Rather, it means that the two quantities are of equal magnitude but opposite sign. Which makes sense. Energy transfer is directional. If one loses energy, the other must gain it. The bottom line is the energy is transferring between a system and its surroundings, and it could go either way. So, how does a system exchange energy with its surroundings? One way is to exchange heat. In this sense, heat is a quantity of energy. Now, don't mistake heat for temperature. While an injection of heat can change the kinetic energy of a material, and thus its temperature, it can also change the potential energy of a system. So again, it is a quantity of energy. Heat is given the symbol Q. Unfortunately, we used lowercase q before for charge in Coulomb's law, but in thermodynamics, Q is heat. The sign of the value of Q indicates in which direction heat is transferring. If Q for the system is positive, we say that heat is being absorbed by the system. If Q for the system is negative, we say that heat is being released by the system. We can think of the system as a bank, where energy can be deposited or withdrawn. If heat transfers from these surroundings into the system, like a deposit, heat is absorbed by the system. The value of Q is positive, and delta E for the system is also positive. In other words, the energy of the system increases when it absorbs heat. Of course, energy transfer could go the other way, like a withdrawal. If heat transfers from the system into the surroundings, heat is released by the system. The value of Q is negative, and delta E of the system is negative. The energy of the system goes down. Note that from the point of view of the surroundings, the signs would be opposite. Energy can also transfer between system and surroundings by work. Technically, work is done when a mass is moved some distance. Imagine yourself doing work, such as moving furniture all day. At the end, do you have more energy or less energy? Naturally, when you, a system, do work, your energy goes down. Work is given the symbol W, and again, the sign is important. If W of the system is negative, we say that work is being done by the system. If the value of W is positive, we say that work is being done on the system. Back to our bank picture of the system. If work is done by the system, it is like a withdrawal of energy that goes into the surroundings. Much like you moving furniture, W is negative, and the energy content of the system goes down, so delta E of the system is negative. If work is done on the system, the value of W is positive. Energy is put into the system. Delta E of the system is positive. Note that with heat, the important words are whether heat is absorbed or released by the system. With work, the important words are whether work is being done on or by the system. Since energy can be transferred by heat, by work, or by both, the total energy change of the system is the sum of Q and W. Keep in mind that Q can be positive or negative, and W can be positive or negative. It's very important to keep track of signs in thermodynamics. The unit of energy that we will use is the joule, or the kilojoule. The calorie is another common unit, but we'll stick to joules. Let's try a couple of examples. What is the value of delta E when 100 joules of heat is absorbed by the system and 200 joules of work is done on the system? The key is to determine the signs of Q and W. Since heat is absorbed by the system, the energy content of the system is going up, so Q is positive 100 joules. Since work is being done on the system, the energy of the system is also increasing, so W is also positive. Delta E is then the sum of positive 100 joules plus positive 200 joules, which works out to positive 300 joules. Here is one more example. What is the value of delta E when 700 joules of heat is absorbed by the system and 800 joules of work is being done by the system? Since heat is absorbed, the value of Q is positive 700 joules. Since the system is doing the work, the value of W is negative 800 joules. Delta E of the system is the sum of these two, which comes out to be negative 100 joules. Oh, by the way, for this case, delta E of the surroundings would be positive 100 joules. And, as always, delta E of the universe is 0.